Hi everyone, welcome to this video lecture presentation on relative reaction rates in chemistry. Relative reaction rates, these are also called average rates of change in the concentrations of products and reactants for a given chemical reaction. Now, these are average rates of change, therefore these are the rates for the reaction over a entire time range versus whatever those rates are at any individual point in time. Our generic scenario is always just going to be whether we have 1, 2, or 3 reactants or products. Some generic scenario is A and B react together to get C and D, and their stoichiometric coefficients are lowercase a, b, c, and d. Anytime you see relative reaction rates, the one thing that you can be expected to do is to develop an expression between the rates of each chemical species, each reactant, and each product. And to do this, the first thing is always have the Greek letter delta, that triangle, as part of the rate of change for each chemical species. To write the rate, that would be delta concentration over delta T. Concentration represented with brackets. So to write the rate of change for reactant A, that would be delta bracket A bracket over delta T. And then we would just write those rates for each reactant and product, A, B, C, and D. Now, the rates themselves are not equal to each other, but they're relative based off of constant factors. When it comes to relative reactant rates, these constants that we multiply by the rate to get them all equal to each other is the reciprocal of their respective stoichiometric coefficients. So, for example, to what we would multiply by the rate of change of A, we would multiply that by 1 over little a, or whatever its stoichiometry was. And we would do the same thing with the rate of change for B. We would multiply that by 1 over B. We would multiply the rate of production of C by 1 over C, and the rate of production of D by 1 over D. Now, while all these are rates of change, when it comes to reactants, those are rates of change that are consumption. They will be consumed with time, so their rates of change are negative. Whereas with the products, those rates of change are rates of production. Therefore, their concentration is increasing with time. Their rates are positive. We can't just have a rate of change, a rate of production which is positive, multiplied by a positive fraction equal a negative rate of consumption multiplied by a fraction, unless we make that fraction negative. Therefore, anytime you have a reactance, since its rate of change is going to be a negative value, we'll have to make the reciprocal a negative reciprocal. That way, a negative value times a negative value will be positive, and that will allow us to still equal any of these expressions on the product side. Delta A over delta T, that just is the molar rate of change of A with respect to time. How is its concentration changing? And those fractions, they're just the reciprocals of the stoichiometric coefficients. But they were made negative if they were if they were from reactants. Whenever you have relative reaction rates, there's usually 3 steps. The first step is balance the chemical equation you're given if it isn't already. The second step is to write that long expression of how all the different rates are relatively equal to each other. And then if you are given the rate of change for any one of those chemical species, solve for the rest. One example being the decomposition of phosphorus pentachloride into P4 and molecular chlorine. Well, to balance that chemical equation, that would be 4 molecules of PCl5 break down into 1 molecule of P4 and 10 molecules of Cl2. Therefore, the rates of change, the average rates of change expression would just be -1/4 the rate of change of PCl5 equal to 1/1 multiplied by the rate of change of P4 with time equal to 1/10 times the rate of change of Cl2 with time. That negative in front of the 1/4 is because that is a reciprocal of a stoichiometry from a reactant. Now let's say that we're told the rate of change of PCl5 was -0.1 molars per second. If that's given to us, then what are the other rates of change for the other chemical reactants? Well, when we're given that value, just go to your expression and replace the rate of change that we were given with its value. So instead of delta PCl5 over delta T, we'll replace that with -0.10 molars per second. Therefore, that times -1/4 gives us 0.025 molars per second. And that is set equal to the rate of change of P4 times its reciprocal fraction, which would also be equal to the rate of change of Cl2 and its reciprocal fraction. Now, to find the rates of change of P4 and Cl2, it's just a little bit of multiplication. Getting P4 over T by itself, well, since it was just multiplied by 1/1, that just means that the rate of change of P4 is 0.025 molars per second. Now, since 1/10 times the rate of change of Cl2 equals 0.025 molars per second, multiply both sides by 10 to get the rate of change of Cl2 with respect to time equaling 0.25 molars per second. All right, so that would be how to get the two relative rates of change for P4 and Cl2 based off of the other one we were given. One other equation, one other scenario, let's say we're given the balanced chemical equation. Lithium phosphide reacts with 3 molecules of sodium cyanide to produce 3 lithium cyanides and 1 sodium phosphide. If you're asked to write the relative rate expression, that would just be the second line. Negative change in lithium phosphide equals -1/3 times the rate of change of sodium cyanide equals 1/3 times the rate of change of lithium cyanide equals 1 times the rate of change of sodium phosphide. Remember that even though lithium phosphide had a stoichiometry of 1 and 1/1 doesn't need to be written, we still need to times this rate of change by a -1, just because it is a product or a reactants rate of change. Now, if the rate of change of lithium cyanide is 0.6 molars per hour, we can use that to solve for the remaining three rates of change for the other chemical species. And to do that, we're just going to go to lithium cyanide, where its part of the relative rate expression is multiplied by 1/3. Therefore, we're going to take 1/3 multiplied by 0.6 molars per hour, the rate of change of lithium cyanide. And that together gives us 0.2 molars per hour. Therefore, 0.2 molars per hour is what all three other parts of our relative rate expression can be set equal to. -1 times lithium phosphide times the rate of change of lithium phosphide equals 0.2 molars per hour. Therefore, the rate of change of lithium phosphide is negative 0.2 molars per hour. The negative 1/3 times the rate of change of sodium cyanide equals 0.2 molars per hour. The rate of change of sodium cyanide is therefore negative 0.6 molars per hour. And with sodium phosphide, as we set it equal to 0.2 molars per hour, we already have our answer. Lastly, there are some factors that can affect the relative rates of reaction. These are average rates of change. Therefore, whatever can change how quickly a reaction gets from start to finish, or how slowly it gets from start to finish, will affect its average rate. And four factors, there are more, but four factors that are common to talk about. There's temperature, such as in the top left example, a sugar cube in water. It takes a while to simply dissolve unless you increase the temperature. That increases the kinetic energy of the molecules inside that solution, therefore increasing its energy to dissolve into the water. There's also two similarly connected factors, surface area and concentration. Surface area in the scenario of if you were to take that cube and crush it, then there are many more pieces or many more areas of contact for water molecules to surround those sugar molecules, break them apart from each other, and dissolve them into water. That's essentially increased collisions due to temperature range or through crushing it. There is also concentration, which is similar to surface area. Say in the bottom example, you start with just a certain amount of reactant A and B, and it might take a certain rate, a certain amount of time for them to interact, to collide. But if you were to say double the concentration of A, triple the concentration of B, that causes more surface area for A and B to find each other, or think of it as it increases the potential for collisions to happen. And you can also add a catalyst, which those are meant to speed up reactions by shortening their initial energy input necessary to get the reaction from reactants to products by minimizing the activation energy barrier. In any case, around the 15-minute mark, that's the lecture on relative reaction rates. Glad to have you all, and peace.